Okay, let's go ahead and get started. So to get started, there is one question on the exam. It was one of the first questions. What was the number?
Number 2.
2. Dealing with the number of unpaired electrons. Yeah, and it's ambiguous in the question whether or not that's a ground state configuration or hybridized. So if you answered either 4 or 2.
Yes, okay. Give me high points back!
Except for Ava.
I flipping will bite you.
Wrong weight class. 10 demerits for Ava's group. Hufflepuff.
Yeah.
Yeah.
No,
Yeah. So where was I? Oh, just if you have the exam, come up after class and I'll get your name and I can get the extra point on. If you don't have the exam, bring it in on Wednesday and show me and I'll get your name. And we'll get those points adjusted.
Sorry for the morning aggressiveness. I just got really excited.
That's... OChem has a way of getting people passionate about things sometimes. So, speaking of exciting things, let's get back to Chapter 6 with chemistry associated with alkenes. So, to quickly review what we've done so far with reactions, if we've got some general terminal alkene here, and we want to react this with water. Typically, water is inert because it's a poor acid, but if we add an acid catalyst in a reversible reaction, in this case, sulfuric acid, a couple drops of sulfuric acid will kick this off. What we'll get is the hydroxyl group from the water adding to the more substituted carbon. And a proton adding to the less substituted carbon. So if we were looking at this mechanistically, what's taking place, I'm going to use the sulfuric acid mechanism. What we have is we've got our extra electrical density around the pi bond. We have this very acidic proton, it's a strong acid, so it's very comfortable losing the conjugate base. We can get a nucleophilic attack where these electrons come in, attack the proton, that exceeds the duet, which pushes these bonding electrons to the conjugate base. And this is going to be a slow step, a reversible process. This proton is going to get located on the less substituted carbon because the cation that's formed is going to need to go to the more substituted carbon. I'm just going to put it in a CH3 instead of drawing it as its own. At some point, we can get off of the baby steps of showing the proton added discretely and just put it up as a CH3, and that's fine. And then once we've got this, we have is an attack from water, where water acts as the nucleophile, because this is a carbocation and it is reactive, it is not happy. So these electrons are going to come in, attack the carbon, but this is going to be reversible also, but it's going to be our fast reversible step. When this happens, we have to retain the net charge for the system. So because we have a cation here and we don't have any charge here, we have to have a net cation in our product. And this isn't our alcohol product, but because this is acid catalyzed, we can reform an acid catalyst very easily. So we can come in with another equivalent of water, and this equivalent of water Lone pair can attack the proton, very acidic, breaking this bond, pushing the electrons to that oxygen, satisfying the positive charge. This is going to be a second fast step. And we form hydronium, which is where our charge ends up. So we start with an acid and we end with an acid. That's why it's an acid catalyst. Because the acid isn't actually being consumed. It's being initially consumed and then reproduced. So not consuming any of the acid in this reaction. This is just how we do an addition of water across an alkene under acidic conditions. Now, we can do this reaction, a very similar reaction for things other than water. We can add alcohols in the same fashion. Instead of adding water, we can add methanol. We could add ethanol. We could add any alcohol in the same fashion. And to make this really work plausibly, in the same way that we would be doing this reaction in an aqueous system, we would be doing this reaction in a solution of methanol, if we were trying to add methanol. And let's take a look at that really fast, what that looks like. It's very, very similar, but instead of adding water, let's add methanol as our alcohol. Actually, let's just add a generic alcohol. That's a nice way to go. And what we'll see is that instead of having a hydroxyl here, we'll have the conjugate base to the alcohol attached, and we'll have the hydrogen added to the less substituted carbon. So the mechanism is nearly identical. It is mechanistically identical. It's just that we've substituted a different nucleophile-electrophile pair. So let's see. We've got our first step doesn't change. We've got our acid. Strong acid can get attacked, breaking the bond, pushing the electrons to our conjugate. This is going to be a slow step again. We're going to have to put the cation where? The more or less substituted carbon for the cation.
Less. One has less hydrogens.
Cool. So the proton is going to be added to the less substituted carbon. And by less substitute, I mean primary, secondary, tertiary. So because the secondary carbon is going to be more substituted in terms of carbon-carbon bonds, therefore it's going to be getting the cation. We'll put the hydrogen here, and then we can come in, and instead of reacting with water, because we have a different solvent now, notice the only difference is the R group instead of the second proton. We can do the same style reaction. We're going to get our fast reversible reaction. We have to retain a positive charge because we don't have any extra electrons in the party to get rid of it. So because this is giving up an electron to form a new bond, the positive charge goes here. And then another equivalent of alcohol can come in, just like water before, take that very acidic proton, breaks this bond, pushes those electrons up to satisfy the positive charge with a second fast reversible step. And here we have an ether. And so the ether is this carbon-oxygen-carbon motif, which we have here with carbon to oxygen to other carbon. And like I said, we could do this with methanol, ethanol, propanol, any of the liquid alcohols that we could use as a reaction medium for this. So hopefully everyone sees how incredibly similar this mechanism is. Yes?
So what happens to that last ROH that you just added another H to? You don't have to put that as a final product?
Oh, no, that's regenerating our acid catalyst.
So that's...
So we could say
Because
plus.
they're not the same...
Yeah,
it's not
but
the same
when we
thing,
put
what you
this
did.
sulfuric acid into an alcohol, it's going to reversibly form that as a product anyway.
Did you drop a 4 to a 3?
I did.
Cool. Just checking if I was like, you were just like moving
No.
it like through another step.
Nope, nope.
Cool.
There's
Cool.
didn't lose an oxygen there.
I'm
Cool.
just assuming the H is disassociated with floating around.
If that's what works psychologically for you, then you can. But that doesn't justify the formation of the alkoxide product here. And this is very, very similar to this in terms of its acidity. Some of them are a little more acidic than hydronium. Some of them are a little less, but a little more acidic. This also introduces things that will become really important in lab when you're doing these kinds of reactions. It's really hard to get certain alcohols really dry. Alcohols tend to be hygroscopic. Getting them to 100% purity or 100% free of water is challenging. And because of that, when you distill them, for instance, they form azeotropes and they pull water with them. It's sometimes challenging to get very pure alcohols. So sometimes there'll be trace water in these solutions, and you can get byproducts because of that. Because if there's water in solution, it's going to be competitive as part of this reaction. If you have a lot of water, you're going to have a more significant contamination of byproducts. Yeah.
What's determining the slow versus fast, the rate? The rate, like what's making that slow versus fast?
Oh, it's just that has to do with the energetic barrier. So whenever you have a tall energetic barrier, it's going to be a slower step. And also, not only is it slow, but it's not preferred. So this is not a stable preferred. If you only drew this part of the reaction, this would not be favored as a product. This would be, the reactant would be favored in the equilibrium system. However, because of Le Chatelier's principle, because of subsequent reaction with this, we're pulling this out of solution quickly, because this will rapidly react with your alcohol to form this product followed by this product. So we're effectively taking the product out as we form it. So even though it's not preferred, it keeps forming, albeit a little slowly. And then as fast as it's formed, it's consumed and taken downstream. Yes?
We were pushing electrons to the alkenes, the H turns a 4 to be here, it's going to be S to the oxygen. In the book, they have it toward oxygen.
Technically, it goes to the oxygen, yeah, because it's going to have that extra double bond in resonance and charge, but the charge is going to be distributed. So whenever you have it's a good question. Whenever you have an ion, let's say, like if we do chloride, you know where the charge is that's on the chlorine. If we are on a hydroxyl, you can pretty much locate the charge on the most electronegative atom here. What if we have something like that? can say that the charge is located on the oxygen that we drew it on because of the formal charge associated with it. With this having a formal charge of 0, this being a formal charge of 0. But this is all resonance stabilized. We could put the charge here, or we could push it back here, put it on here. We could put that charge on any of these 3 oxygens, which is why it's a stable place to put the charge, because we're distributing over 3 different locations, which is why sulfuric acid's a strong acid. It's not incorrect to do that either. Which is why you say, and we're putting the electrons over here, because they're actually going to be distributed over 3 locations.
So is sulfuric acid a stronger
Yes.
acid than a protonated alcohol, or are they roughly the same?
Sulfuric acid fully dissociates in water, and it will nearly fully dissociate in most of these liquid alcohols. Regardless, even if it didn't fully dissociate, the way hydrofluoric acid doesn't fully dissociate, it's still, although it's not a strong acid, potentially it's a very, it's acidic enough where it will predominantly dissociate and do these reactions. So you can consider this an equilibrium system that potentially favors reaction. Oh, wait, that should have been that arrow, not the plus sign. Like that. Once again, and as fast as this, and it does take, because it's acid catalysis, you just have to have enough catalyst present where it sees it so that it can propagate. Good questions. Yeah.
Just checking for the sake of making sure I don't mess up in the future.
Yeah.
Because you guys showed the lone pairs at the beginning. Do we need to show the lone pairs on the OR at the end or not?
I like lone pairs.
Okay. Cool.
Lone pairs are nice.
All right.
Lone pairs are almost always nice. When we're pushing electrons, lone pairs are really nice. Okay, so we've got 2 identical mechanisms. Let's start changing this up a little bit. Oh, no, we're not going to change it up yet. No, we're going to kind of change it up, curveball. So everything we've done so far involves a carbocation intermediate, where we're putting the carbocation on the more substituted carbon because of hyperconjugation. There's a problem with carbocations. Carbocations are subject to structural rearrangements, both by 1,2 hydride shifts and 1,2 methyl shifts. So the issue with carbocation is it will rearrange to form a more stable carbocation, if it can. And this is going to result in combinations of products if you have, and this is the whole thing, if it can. So let's take a look at what that looks like. There's 2 ways it can do it. We can do it through a 1,2 hydride shift and a 1,2 methyl shift. So a hydride is a hydrogen with a lone pair and a negative charge. Extremely basic, very reactive. Reactive enough to pull water apart. Much more basic than hydroxide. So let's see here, a good example. And let's just form a carbocation generally by reacting this with hydrobromic acid. Well, so far, based on what we've done, we would recognize, okay, we have this nucleophile in the double bond. We have an electrophile in this hydrogen. So we can take these electrons, attack this proton, break this bond, push those electrons to the bromine, forming a bromide. Because it's a nice stable leaving group that can accept those, gets noble gas configuration, and redraw. And this would be what we would predict to form. Now, under normal circumstances, what we would assume would happen would be that the bromide would then come in and do a second attack on the carbocation and put the bromine on the more substituted carbon. Yes?
The positive carbon there that
Needs another hydrogen. Yeah, it needs another hydrogen. So we would get that second attack right there. However, that happens, but just not predominantly. We have a competitive reaction. What we also see is because this is, what kind of carbon is this? Carbocation. Is this primary, secondary, tertiary?
Secondary.
Okay, so we got a secondary carbocation here. What can happen is these electrons, because if you have a hydrogen which can move across one bond from carbon to carbon. Now, sometimes when we introduce this, people get a little excited and they start pulling hydrogens from all over the place. It can only come from one carbon away. It has to be a 1-2 shift. This electron pair can cease binding to this carbon and hop to this carbon. And when that happens, this carbon becomes a carbocation. Now, what that looks like is this, and this happens because by doing so we form a tertiary carbocation, which is much more stable than the secondary carbocation.
Okay, so the hydrogen on the tertiary carbon wants to go to the secondary carbon.
And that's, yes, and that happens because we're going from a secondary carbocation to a tertiary,
Okay.
which is more stable. So whenever you can do a shift that results in a more stable product, it will happen. You won't 100% get this because you now have a competing system where the bromide can attack here and will simultaneously attack this that hasn't shifted.
So you get like a
You're going to get a mixture of products. Yeah. So any time we're doing reactions, and this we're going to down the road here get more tools in our toolbox, there's limitations to any reaction, both in terms of stereochemistry and mixtures of products and side products. And if you have a setup where you have an alkene next to a highly substituted carbon, there's very good odds that you're going to be getting these 1,2 hydride shifts. So you have to be cognizant of any mechanism that has a carbocation. If you're asked to predict what the product is, this is a very fair question. If you were to ask what the major product is, the major product would be
because it's more stable.
because that intermediate is going to, that carbocation intermediate is going to predominantly form and then get attacked by the bromine more frequently than this one. If you're asked to predict the minor product, that would be the minor product in the back.
Can you be asked to find the reactant from something that's undergone a shift?
Totally fair. Yeah. You can be asked to reverse engineer this.
Okay, and if that's
More importantly, you can be asked to, more specifically, if this was a desired product, what reactant could you use to produce it?
When writing out mechanisms for these things, is it proper form just to, there's no way to combine steps, correct? So you should write out each step, like the 1,2 hydride shift should be its own step.
We're going to start combining some steps in a
Okay.
second here. It depends on the philosophy of the book. I like this book because I learned things with, you can see the logic of multiple pushes and pulls in a system. I've seen books where everything's discrete and just takes an enormous amount of space. And it's not wrong. In fact, it might technically be slightly more correct. Like if you look at, I have a couple books in my office that do things like that. It's just, I think when we start to get into larger mechanisms, having something like, if I have a carbonyl with a nucleophile and I attack here, I'm going to push electrons here, and then I'm probably going to do a subsequent attack on some other electrophile here.
But combining like a 1,2 hydride shift or 1,2 methyl shift, can you combine that with the next step, or is that one of the things that's best left separate?
I would separate them so you're really showing that shift.
So if you were to just give us the initial reactant in this, and then that entire thing you were asked what all the products were, would one of the potential answers be if the bromide or halide attached to the primary carbon, or does the fact no?
No, because whenever you have competition between a tertiary and a primary, the difference is so big you can functionally say the primary does not
But
form.
that first one, it's just competition, because that bond has to break first, that's the first step, and that's a competition between a primary and a secondary.
Yeah, but those are reversible steps.
Okay.
So you're going to be seeing multiple competing equilibria, and I would your primary carbocations are just super undesirable.
Yeah, but I know that earlier in the book, like if it was just competition between a primary and a secondary.
And yeah, you're probably going to find a measurable amount of product between a primary and secondary, but it's going to be super minor.
Okay.
So just to be completely clear, if we're asked a question about products, don't put the primary then?
You can say if it's secondary versus primary,
Like in this.
you can say major. Well, this is a tertiary versus secondary,
Okay. Yeah.
so there is a mixture.
Okay.
But the tertiary is favored.
Got it.
But if it's tertiary to primary, say, you can say functionally, you're going to be 99-point-something% tertiary over a primary.
These shifts involve breaking a bond and forming a new one,
Yes,
correct? And it's just that
absolutely.
force is just so strong it breaks a bond.
The force is strong with this one.
Okay.
Yes. So,
Because it just seems counterintuitive.
well, we have a vacant orbital that wants electrons, and we have occupied orbitals which have electrons, and they're right next to each other. And if there's enough chemical rationale to justify moving these to here, then it can happen. And in this case there is, because by doing so we've stabilized this charge. So it's not, yeah. Now, this can also happen, let's say that we don't have a hydrogen there, let's say we've got a methyl. Uh-oh. Well, we can't do a hydride shift now because there's no hydrogen whenever you have a quaternary carbon like this. But when, bless you, what am I doing here? And this isn't specific to just hydrobromic acid. I'm just using hydrobromic acid since we've done this mechanism the most. Any first step which involves a nucleophilic attack from the alkene to anything that gives us a carbocation intermediate, we have to take this into account. Anytime we have carbocation intermediate, we have to worry about 1,2 hydride, 1,2 methyl shift. So here we go, put it here. But now we can't do a hydride shift. Hydride shifts are easier than methyl shifts, but we can't do a hydride shift. But we can just take these electrons and move the entire methyl group over in the same way. And now we have made a tertiary carbocation versus a secondary carbocation. So as a preferred product of the bromide can come in and do our last attack on the tertiary position. So it's, again, if you were asked to find the major product would involve putting the bromide on that carbon versus that carbon. And you'd have to account for the methyl shift. And the only way to do this is to practice. But usually, if I see an alkene and I'm doing this kind of mechanism, I'll look around and be like, okay, do I have a highly substituted carbon nearby? If I do, then I start to think about it. If I don't have a tertiary carbon nearby or quaternary carbon, it's not going to be an issue, and I'm not going to stress it. And for goodness sakes, please don't get so crazy with this that you start trying to make secondary to secondary hops, because that doesn't make any sense chemically. And people do. People get really love hydride shifts. Are like the best thing ever when you're asked to produce something. Like, I'm going to work some hydride shift, methyl shift magic, and pull some things and put them over here, and it has to result in a more stable carbocation. You can't just do a shift. Guys ready for another mechanism? Another reaction? All right. Too much rock for one hand. Okay, so we have a new reaction we're going to add to our toolbox, hydroboration followed by oxidation. Hydroboration is one step. Oxidation of the product of the hydroboration reaction is a second step. So if you're doing this in the laboratory, you would put everything together, you would do one step, then you would do a second step. And what this looks like, just as a generalizable reaction, if we have some alkene and we want to do a hydroboration reaction to this, our first step would be to use borane, which is BH3, in tetrahydrofuran as our solvent, or THF. And then our second step is to use hydrogen peroxide in the presence of base in an aqueous system. So we have peroxide in a very basic aqueous system. And what we get is that, without any stereochemical concerns yet. I'm like, hey, this is the same reaction from just using acidic water. I'm like, well, it can be, but sometimes it will play out differently in terms of where the hydroxyl goes and in terms of not having to worry about carbocation rearrangements. So we'll have some caveats to this reaction that we'll worry about in a few minutes here. So something about borane that is worth noting. It's one of the exceptions to the octet rule, where it is relatively stable with only 6 electrons instead of the full 8. However, because it does not have an octet, and this is a vacant p orbital, it can accept electrons as an electrophile as part of a nucleophilic attack. So at this point, you're thinking, aha, now I know where we're going with this because we have this nucleophile with all this extra electrical density in the alkene pi bond, and now we have an electrophile, so now I can see where this is going to go. And you'd be correct for a little bit, but then it gets counterintuitive pretty fast. So the first step, let's do the mechanism for the first step, the formation of the alkyl borane. yeah. Let's just do it with CH2 for now. So BH3, I'm just going to draw out one of the hydrogens specifically. And what we're going to see is our first nucleophilic attack, where, just as we were talking about, we have this vacant p orbital which can accept electrons. It's electron poor. Here we have extra electrical density in that pi bond, so we get our first attack here. And as soon as we get that attack, the electrons between this boron and hydrogen can then come up and attack the more substituted carbon. And the reason they're going to go to that more substituted carbon is because the carbocation character in the transition state is heavier here, so it's going to form more quickly, so it's going to be the preferred product. Kind of like what we've been talking about already. Yeah, we can do that. So this is called an alkyl borane. Now, how many electrons are around that boron? 6. So it still has a vacant p orbital, which means it can do this again. And that's exactly what's going to happen now, is this can act exactly like this, and we can get another attack from another alkene in exactly the same fashion. And we can do this until all of these hydrogens are replaced with alkyl groups. So instead of BH3, you end up with this Br3. Let's see here, let me just go ahead and draw one of those out. So we've got another equivalent of alkene, and I'm going to draw this in as so we've got our two hydrogens. I've drawn one with the bond, or on the hydrogen, and the R group, with the R group being all of that. Exact same thing happens. And then we can do the same thing again and add our third alkyl group to the alkyl borane. So this is the first step here. Second step, any questions about the first step before we move into the second step?
Okay.
Could you just draw that out, because that's really difficult to visualize with BRH.
Nope, no room. Gonna have to start. Yeah, if we have to be able to use R's to substitute for things, because what this is doesn't matter. What we're doing is we're just taking one of the hydrogens off and putting on this entire group via this new pair of electrons bonding from here to here. Notice this attacks the more substituted carbon.
Okay. Okay.
Right, because of that carbocation character in the transition state, which means the borane attaches to the less substituted carbon. So that's going to be super important in just a second when we start to do the oxidation. We have hands everywhere. I don't even know who was first. I'm just going to work my way left to right.
So is the attachment of the BH2 and the hydrogen, does that happen at the exact same time? So
It's concerted.
Okay. So hydroxide ion can't just come in and take the positive charge.
And there is no hydroxide ion because we are doing the first step discretely with borane and THF.
Okay.
Yeah, if we started throwing this in the mix in the middle, all kinds of silliness would ensue.
Sorry, just clarifying. The bottom section, that's just with PRH. You're not. That's not like the step after the top thing.
So if you have all this, so when you do this, you put in enough of this to where it's going to react with BH3, but then you're going to have BH2R. It still has the vacant p orbital. Another one of these can come and attack this now, and then a third one can come and attack again.
Oh, so you're just showing the R is the one that attacked it, right?
Here. Yeah. Try to unconfuse things.
What is the S?
Oh, see, now I'm doing other things.
Just label
okay.
it R2. Label it R2.
R dash.
Cool.
There we go. Okay.
R dash on the lows.
Yeah. So this is now there.
Okay.
There we go.
So the boron is always going to be the electrophile versus the hydrogen. So the
Yes.
carbon with the most hydrogen is active by.
Well, because we have, so this is our first electrophilic attack, and now we have 8 electrons to play with, but boron's okay. And this has partial cationic character, because as this is breaking, this will get more cationic character because it's more substituted. So as these electrons leave this bond and move here, it'll attack this position because of that increased cationic character on the secondary carbon.
So once you get to the oxidation step, your boron's always going to be completely like substituted with alkyl group.
If you have enough of the reagents in
Okay.
play, yeah.
If you're like doing it correctly, and you're like, okay.
Why does it stop at trialkyl?
Because it's perfectly content to not have a full octet. It's not, yeah. It can, there's a vacant p orbital which can accept electrons, but it's fine as a BH3 or BR3. Okay, guys ready for oxidation? Like, oh yeah, I'm so ready for oxidation. It is 9-something in the morning. Oxidize away. Okay, so just get rid of all this. Oh no, no, get rid of that. Okay, so second step, we've got boron in the center. Got some R groups around here, and we'll just draw one of them in. Let's say it's a CH2, CH3. Got our 2 groups. We're going to come in with our hydroxide. And as you guys can already tell, we have lots of extra electrical density here around the hydroxide. We've got that charge. We have our vacant p orbital. So we can just come in here, attack the boron. This is going to be reversible.
Yeah, thank you.
There we go. Notice the charge has to move also because we are giving up the electrons here. This is neutral. This is gaining electrons, so it has to become negative. So now, you're going, oh, well, that's not happy. What are we going to do? Well, we're going to take these electrons between one of the R groups. I'm just going to do the one that I've drawn it in specifically. And these electrons are going to move over here. Kick that off. And did I get that right? Good. So we're going to take this whole group, like a methyl shift, take those electrons from the bond, put it on this oxygen, and kick off that proton. And we're going to get this. So, I mean, if you guys, I mean, I've done this, I could draw it like, hey, I'm taking these electrons, both of them, and moving them over here, but they're staying attached to this carbon.
Wait, how is it like a methyl shift? Sorry, I didn't catch that.
In terms of just the electrons completely moving and taking something with it, if this was a methyl group, it would just be moving over to another carbon. Different, I mean, just maybe not the best analogy because it's not based on a carbocation. We have extra electrical density in this case. Now this is going to be neutral, and when we move these electrons over the proton, yeah, right.
And then the proton's just floating around.
Oh no, we got a terminus here
Okay.
because we're basic.
Not secret.
Right? So, all right. Here. We got one more step. We got to do. Did I? Son of a gun. You're doing this right. Okay, good. Another attack from hydroxide. I'm going to get used to drawing a boron eventually. You guys see the rationale here? Same issue. We've got extra charge here. We're going to just put these electrons over here. We're going to make an alkoxide. We can make the alkoxide because it's basic because of the hydroxide in solution. And this is going to give us this as a product and this as a product. And then because this is getting a little comical actually by my inability to draw boron. That's what happened to your proton. It formed.
What is that?
Or
is that sorry. Is
or
that
sorry.
like
Sorry. We're not in acid catalyzed. We reform our base. So we just notice we've now put a hydroxyl group on the least substituted carbon. So what we've got going on here with hydroboration oxidation is we're bypassing the entire carbocation intermediate, and we are ending up putting a hydroxyl group on the less substituted position. Now, this happens for one R group, it can happen for the second R group, it can happen subsequently for the third R group. Yeah?
The book in the first step where the document attaches the boron, the book uses peroxide ion.
Okay.
Is it the same results?
Yeah, the book it says you three water H2O.
That's funny. Okay, so what happens when you get, so there's two new things here. We've got peroxide, which is hydrogen peroxide, H2O2. When you put it in a basic solution, you form a very reactive version of peroxide. First step is, it's not just peroxide, it's a activated peroxide.
That's just for the first step.
Yeah.
After
Yeah, that's for the first attack on there. And then everything else is just standard hydroxide pushing arrows.
So would that change the next step?
Only when you're doing subsequent addition of R groups. Each attack forming a new R, putting a new. I don't believe so.
So then where does that second oxygen go? Like in that first step, it would be OH, and then the next step just connected to the boron and just OH. Yeah.
Oh, that's nice. Just reproduces your hydroxide. So that just reproduces your hydroxide in solution, just like a base, like an acid catalyst. It's a basic catalyst. Oh, I'm sorry. What? Ah, there's one.
That second step there, the shift of the alkyl from the boron to the oxygen, that just functions the same as a alkyl methyl shift?
Very similar.
Okay.
Because it's more stabilized by virtue of getting rid of the charge in a place where it's not as happy, and putting the charge terminally onto a hydroxide, which is perfectly content in a basic solution to be there. So if you're trying to push these electrons not in a basic solution, forming hydroxide wouldn't be as favorable as it is in this scenario because we've made a highly basic solution. So reforming base is favorable. So that's hydroboration oxidation. We also have addition of a peroxy acid as a mechanism, and I want to get into that one here. Addition of a peroxy acid is much simpler. So the neat thing about hydroboration oxidation is there's a rationale. We go through the mechanism, so there's a rationale for why we are putting hydroxyl groups on less substituted carbons instead of more substituted carbons, and that we can see that there's no carbocation intermediate that's subject to 1,2-methyl or 1,2-hydride shifts. So if you yeah, exactly. And it says it's recording, but all right, well, sorry online folks.